Hello everyone, welcome to my talk Bottleneck Convex Subsets, Finding K Large Convex Sets in a Point Set. I am Debajyoti Mondal and this is a joint work with Stephane Durocher, Mark Keil and Saeed Mehrabi. We are from the University of Manitoba, University of Saskatchewan and Carleton University. As you can see, we are trying to find K large convex sets in a point set. And in 1980, Chavatal and Klinczek showed that in order n cubed time and in a squared space, you can find such a largest convex point set. For example, here you have an input and you can have a largest point set where the convex half containing 6 points in the output. Later on, this was improved to order n space in 1989. What we are trying to do in this paper is to generalize this problem to K convex point sets. For example, here you have an input where on the left you have a point set P and you are given an integer K. If K is 1, you are trying to find one largest convex point set. If K is 2, you are trying to find two largest convex point sets. Now, when K equal 2, then we are actually trying to maximize the cardinality of the smallest convex set. If we look at the input here, we have 10 points in the input, and the output, when K is equal to 2, I have two convex point sets where each set containing 5 points. Now, in this setting, you cannot do any better than that. For K equal to 2, the best possible scenario is both of your point sets are large and the minimum cardinality is maximized when each convex set contains 5 points. Now you can have K equal 3, 4, and so on. We call these sets as bottleneck convex subsets. So again, the problem input is a set of n points and an integer K, and the task is to find K pairwise disjoint convex subsets of the input point set such that the cardinality of the smallest subset is maximized. Our contribution in this paper is a polynomial time algorithm to solve this bottleneck convex subset problem for any fixed K. We also show that if K is an arbitrary input parameter, then the problem is NP-hard. And finally, we show a fixed parameter tractable algorithm for this problem, where the parameter that we use is the number of points interior of the convex hull of the input point set. Now let's see some related research. We have already seen that for finding the largest convex point set, we have a polynomial time algorithm. But there are other research results that provides us with some bounds. For example, in 1935, Arder-Sakharov's theorem implies that every point set contains a convex log n gon, so we can find a fairly large subset which is convex. Now, Urobe repeatedly applied this theorem to partition the point set into n over log n convex subsets. Now, there is another problem which is called Ramsey remainder problem. And that problem actually implies that if K is smaller than equal to n minus Ramsey remainder over K, then we can find convex subsets such that each of them are size at least K. So all these theorems provides us with some bounds, but that do not solve our problem exactly. There are other research results in terms of convex cover number. So in this case, we want to cover the point set, the input point set, with minimum number of disjoint convex sets. In this case, we can see that the input has been covered with two disjoint convex sets. You can see that we cannot cover the input point set with less than two convex sets. So this is the minimum possible. In this case, the convex cover number is 2. Arkin et al. Said that the convex cover number of a point set is NP-hard. They also gave a polynomial time log n approximation for finding the convex cover number. This problem feels similar to our problem, bottleneck convex subsets, but the objectives are different. Here we want to minimize the number of convex sets, but in our problem, in the bottleneck convex subset problem, we are given the number of convex sets we want to have, but we try to maximize the cardinality of the minimum convex set. Well, so now there are some more research results, which is for large K. Now, if you think that we have a point set of n points and we want to find n over 3 convex sets, then it is easy because based on the cardinality of the point set, we can partition it equally with 3 points each or 2 points each. And this reduces into some case analysis and we can really solve the problem. But as soon as K goes to n over 4, then the problem becomes non-trivial. Karaoke showed that there is this n log n time algorithm that given 4 endpoints can partition the point set into sets of 4, and those sets of 4 are convex quadrilaterals. The algorithm can decide whether this is possible or not. For example, in this case, we can have the partition. So this is a satisfiable instance where you have 2 convex sets. Each set is a convex quadrilateral. Now, if you have n points for k equal n over 4, you can decide the bottleneck convex subset problem in polynomial time. So again, we have some case analysis that gives us this final result for bottleneck convex subset, but these all results are kind of limited. None of them gives us a comprehensive idea of what will be the complexity when k is not large, not small, somewhere in between. Now let's take a look at the problem we are trying to solve again. So we have a given set of points as input, and we want to have k convex point sets and try to maximize the cardinality of the smallest subset. We want to first show that there is a polynomial time algorithm that can solve this problem for any fixed k. So if k is fixed small values, then practically we can solve it. So let's see how we can design such an algorithm. So the key idea is this observation. If you process your points from left to right and assume that on the left you have a partial solution with k convex set, assume that k equals 3, and in this case we have 3 convex sets here. And now we want to see how we can extend these convex point sets that we already have on the left to include some points on the right. Now you can see there are lots of options to include, and we try it out, and this actually helps us to devise a dynamic programming because we have only order of n to the power k feasible options to extend these convex sets. But to do it systematically, we actually rely on a graph. What we do is we actually imagine vertical slabs by thinking of vertical lines through these points, and we process the slabs one after the other and create a graph like this. So assume that you are processing this blue slab here, and you have the partial solution which is shown in the middle. In this case, you can encode the whole status here using encoding where you only think of what are the top and bottom edges for each convex set. Now that gives you a configuration as you can see it as a vertex. And now you can think of this vertex and how you can extend this vertex. In this particular case, you can see 2 options. One is including this and the other is including that. And it can actually end like by adding an edge over there. That means you have multiple options here, and you can create an edge from the previous slab to the next slab based on the feasibility. This gives us a directed graph. Now, after we do it for all possible slabs and all possible configuration, we get a graph which is of size order n to the power 5k plus 3. And we can show that a solution can be found by using a breadth first search on this graph. Finally, we end up with this theorem that given a set of endpoints and a positive integer k, the bottleneck convex subset can be solved in n to the power 5k plus 3 time. This ends our first contribution. The next one is that we show that the problem is NP-hard when k is an arbitrary input parameter. The idea of showing this NP-hardness is first to reduce an NP-hard problem, numerical three-dimensional matching, to an intermediate problem which we call angle partition. Then we reduce angle partition to bottleneck convex subsets. Now let's see what is the numerical three-dimensional matching problem. In this problem, you have three sets as input. Each set contains n distinct positive integers. For example, here you can see the sets A, B, C, each containing three positive integers. Now, the task is to decide whether there exist n triples AI, Bj, Ck such that Ai plus Bj is equal to Ck. In this case, you can see that we have an output where 16 plus 12 is 28, then 14 plus 6 is 20, 10 plus 8 is 18. We want to reduce this to the angle partition problem, which is as follows. You have three endpoints on a line, as you can see here, and the task is to find y monotone angles. You can see here we have a bunch of angles, and there is another constraint that none of these angles can be right facing. So what does it mean? Every angle should point towards the left. It will contain this ray going to the right. And we want to show that the numerical three-dimensional matching can be reduced to angle partition. So what we do is for every input instance of numerical three-dimensional matching, show how to construct an instance of angle partition. And finally, we show that there is a solution to the numerical three-dimensional matching if and only if you can find n angles which are y monotone and none of them are right facing. Then we move on to the bottleneck convex subsets problem. We show that angle partition problem can be reduced to our problem. So how do we do it? Given an instance of three endpoints on three lines, which is the angle partition instance, we construct another point set. The idea is to take the input point set, copy it here, and then add some extra points. Intuitively, each of these will create some convex subsets in the original solution. Now, let's see. If there is an angle partition, we know that the satisfiable solution are not right facing. So we can actually extend it to create convex subsets, and we can show that you can exactly partition with n convex subsets, each containing 4n plus 7 points. And on the opposite direction, if there is a solution of the bottleneck convex subsets, then we show that each convex subset must contain these big convex subsets. Since the solution must contain this, to cover all the points here so that we have a balanced partition which maximizes the minimum cardinality, each of these must have 3 points from the left. And there we get the partition of the point set with convex y monotone angles where none of them are right facing. And that gives us a solution for the angle partition. And this concludes the NP hardness proof. And now we move on to the fixed parameter tractable algorithm. In the fixed parameter tractable algorithm, we use the parameter R, which is the number of points interior to the convex hull. Now we want to give a FR times n to the power order on time algorithm. You can see for this example, we have 8 points inside the convex hull of the point set, so R is equal to 8. Now let's see how we can design an algorithm where we take R as the fixed parameter. The idea is to guess the structure of at most k convex sets. Now we know that we are looking for k convex sets, so we think how the k convex set may look like inside the convex hull of the given point set. In this example, we are looking for 4 convex sets, and we guess that 3 of these convex sets takes this structure in the interior of the convex hull. So you have one partial blue convex set, one partial red convex set, and all partial yellow convex set. And now we know that we have this structure that we guessed. We also guessed the size delta of the minimum convex set in the solution. So if your guess is 5, if delta is 5, then we know that this blue convex set, which already contains 3 points, need to have 2 more points. And we determine this demand for every other convex sets that we guessed. So after we determine this structure or guess the structure and also guess the size, compute the demand, we actually model the whole problem using a maximum flow problem. What we do is we create an auxiliary graph where these partial convex subsets are vertices like V1, V2, V3, and then we use these convex hull points as sinks. Now we have a production of delta minus x units for each of these inner vertices, and each convex hull point acts as a sink that can consume 1 unit of flow. Now, after we solve the maximum flow problem, we can turn these into convex subsets, as you can see on the right. Now, the overall time complexity becomes a function of R times Gn times log n, where the first term R to the power k plus 2 stands for the gauges, and Gn stands for computing the maximum flow, and then this log n is because we guess the solution, so you have to do a binary search and guess and verify. And that concludes the discussion on the fixed parameter tractable algorithm. There are many exciting open problems that remains. For example, we gave a polynomial time algorithm for our problem for any fixed k. But we do not know whether there is a fixed parameter tractable algorithm when we parameterize by this parameter k. So our algorithm's complexity is n to the power order k. But can we find a fixed parameter tractable algorithm of complexity function of k times n to the power order 1? And then we showed that the problem is NP-hard when k is an arbitrary input parameter, but we do not know whether we can restrict k to be large. What happens if we restrict k to be theta n? We do not know whether this case is also NP-hard. And finally, we had a fixed parameter tractable algorithm when you used the number of points inside the convex hull as input parameter. But how about other point set parameters, such as the number of convex layers of the point set or minimum line cover number, that is the number of lines that is required to cover the point set? If we use those as parameters, can we have fixed parameter tractable algorithms? It will be exciting if we can solve some of these open problems. And that concludes my talk. Thanks everyone for your kind attention.